Okay, see, okay. So what I was saying is this, see, we will start today with something called cyclic process, which is not difficult, you can understand. I have to draw a graph for that, and then I think you'll understand what's going on. Okay, see, again, this is a PV indicator diagram. That means this is pressure axis and this is volume axis. I can also indicate timing or temperatures at any point of time. Okay, so let's say a gas starts from this state, okay, a state called A, where the volume of the gas is this one, okay, V1, okay, and pressure of the gas at this state, okay, is P1. Okay, so these are starting of state of a gas. It has certain volume and certain pressure. Okay, let's also indicate certain temperature called T1. Okay, then the gas goes to another state, let's say called B. Okay, this is your state B, and how the gas has reached here, okay, it can be anything, but obviously we know, okay, under this condition, okay, definitely I'm talking about expansion right now. So B means expansion. Let's say this is the path followed by the gas. Okay, that means the gas is undergoing change but following this path. Okay, let's call it path number 1. Okay, so what has happened to the gas is expanding, not a problem, you can understand with the diagram. It is not isothermal in this case. You can see the gas pressure is decreasing, but not how it should decrease like isothermal case, right? Isothermal, it decreases like that, okay, the pressure, but this time I'm just indicating any other kind of process. Okay, so the temperature in a state called B, right, can be a temperature T2 when the state is B, and you can also check the volume has changed to V2 and the pressure has changed to P2. Okay, I've been doing this all the time, and very important graph that we used to draw. Okay, so now see, what I'm trying to tell you is this. So at a certain time called T1, the gas was in state A, and after certain time, okay, some changes has taken place. Now gas is a totally different state where the volume of the gas is different, the temperature of the gas is different, even the pressure of the gas is different. Okay, now suppose we do again make some changes to the gas, okay, such that the gas goes back to the initial state. Okay, so you look at this. After reaching a state called B, okay, having different volume and different pressure, I am making the gas to go and reach back to the initial state of initial pressure P1, initial volume V1. You can check the arrow, indicates that the gas is now going from state B to the state A or the initial state A. Okay, this kind of process, okay, you can see the gas has returned to the original condition, okay, original state. This kind of process we are going to call them what process, guys? Yes, waiting for your response. Don't be lazy. Cyclic process. Okay, cyclic process means simply a gas will start from certain state, certain pressure, certain volume, certain temperature. It will undergo a change, but it will go back to the initial pressure and temperature, right? So you get back to the initial state of the gas. Okay, so this process, right, that I'm talking right now, we call it cyclic process. Okay, now what question they may just ask you from here is this. Say, they may ask you how much work is done during a cyclic process. Okay, so we are going to calculate that right now. Okay, it's a very simple one, don't worry about this. Okay, but let me indicate some of the points here. Okay, see, let's call, instead of 1 here, okay, I'm going to give some other points names there. Let's call it C, let's call it D, let's call this one B dash, this point let's call it A dash. Okay, it is below A, so I'm calling it A dash, and yeah, I think we are fine right now. Okay, so just check. See, so check. Okay, how much is the total work done? That is what we are going to calculate during any cyclic process now. Okay, see, so first I will tell you, let's say the gas has gone from a state from A to a state called B. Okay, so when this happens, okay, when the gas goes from a state A to state B, let's forget about this arrow right now. Okay, going from B to A, no, so let's talk about this process here, going from A to B. Okay, can you tell me, guys, how much is the work done? How do I calculate work done in this case? By looking at the graph, of course.
So area under
the area under, yeah, this one, look at this. This is the area under this graph right now. This area, whatever is the value of this area is, okay, that represents the amount of work done during this process of the gas going from a state A to a state B. Okay, so I am going to write that down right now, just check. Okay, see, so waiting, guys. So work done by the gas during the process or during the change from state A to state B, right, equals to how much, guys? It is nothing but represented by area under this graph. Okay, check how am I writing the area under the graph. Okay, see, I'm going to write area of A C B then I have to go to B dash, then I have to go to A dash, and then I have to go to back to A. Okay, that means I'm going like this. See guys, I'm going from here to here, then I'm going from here to here, then I'm going from here to here, okay, A dash, and then finally I'm going back to A. Okay, so whatever I've indicated right now, okay, whatever I have indicated right now represents what, guys? The area under this graph called AB. Okay, and that is your work done during this process going of the gas going from A to B state. Okay, I think this part is clear. Check guys, is it okay? This one. Yes, waiting.
Yes, sir.
All of you
Yes,
waiting.
sir.
Yes, sir.
Those who joined late, so sorry. Okay, I already started, because 8 o'clock no was the timing, so sorry. Okay, by the way, one more thing, what do you think, this work done is positive or negative? Work done by the gas, by the gas, what do you think, the gas is expanding or not expanding?
Positive.
It is expanding, no? So the work done is by the gas or not by the gas? It is really work done by the gas, so it is going to be positive. Okay, if you remember, this is what we have done last time. Okay, now check, I told you just now, there's always this can happen, right? The gas can go back to the what state, guys? Initial state. Okay, following this path called BDA. Okay, so when the gas goes back to the original state, now I am going to calculate work done by the gas in going from a state B to a state A, but obviously following the path called D. Okay, so when this happens, okay, you tell me now how much is the work done, guys? Is it the area under the graph again or not?
Yes, sir.
Okay, but this time,
Yes, sir.
will it be area under the whole graph or just below this BDA graph?
So just
Just
BDA.
below the BDA graph. Okay, this is D here, see, this is D. Okay, so this is BDA. Let me show you again properly. This is BDA. The area under that graph, okay, represents the work done by the gas in going from a state B towards a state A. Okay, so how much is that area? Can you tell me? I'm going to write here. Area under which graph, guys? BDA. So what is that area? Can I write?
A dash B.
Okay, that is fine. So you are saying this area, okay, this one area we have to include right now. Okay, so just like say, so you are saying B, okay, or you said A. We can start with A also, not a problem. Let's start with A then. Okay, say, so A, then what should I write? A dash. You are saying A dash, yes. Then I should write B dash. Then I should write what, guys? B. Then should I go to C or should I go to D, guys?
D.
D. Yes, we should go to D and back to what, guys? A, no? So we have completed, we have taken this area. Let me show you with green marker right now. Okay, very quickly. See, area under this graph, okay, this one is this area. See, A dash, B dash, B, then I have to go to D and then I have to go to A, right? That's, I have covered the area under this graph now. Okay, so in this process, while the gas goes from B to A, okay, that is what we have written there. Okay, now you have to tell me, guys, is this a positive or negative work done by the gas?
Negative.
Negative work done. Okay, because I think you can understand, right? Because it represents expansion or compression.
compression.
Compression. So obviously, right, work done by the gas will be negative, and this obviously represents expansion. Okay, so now if I ask you, okay, what is the total work done by the gas for the entire process? That means entire cyclic process. Okay, that means going from where to where? A to B and from B to A, right? What will be the answer, guys? Will I use these two or not? Will I add them or subtract them? What do you think?
Subtract.
No, add them.
Add.
Total work done, WAB plus WBA. But obviously this is going to be negative, so we are going to subtract the areas. Okay, that is a different thing. But total means always what? Add, no?
Yes,
Okay,
sir.
okay, total means add. Obviously one of them is negative, that's not a problem. Okay, let's try to add. So see, I will do this. I'll take this area, copy, okay, oops, paste. So that is this the first term, okay, and obviously I have the second term. Let me just take it, which is a negative area, copy and paste. Okay, so when I write like that now, okay, now you tell me, what does it indicate, guys? Does it indicate the total area or actually the difference in these two areas?
Difference in area.
Difference in area. Let me show you now what is that difference. Okay, let me show you here in the diagram. Say, okay, check. Okay, I'm going to mark with blue one again. Okay, let me just show you this area. Okay, work done during A to C. Okay, this is the area. Say, from here to here to here, this whole area. Okay, and this area, okay, the work done to go from B to A, right? Let me show you with red, okay, this one. This is the area, right? So are we adding these two areas or subtracting these two areas, guys? Check the total work done. Adding or subtracting?
Subtract.
Subtracting. So if I subtract, what will be I left out with, guys? I'll be left out with the entire area or the area only inside this curves.
Area inside the curve.
I will be left out with only this area, right? Because I have removed this much portion of the area from the entire area, okay? That is the meaning of these two areas that we are subtracting, okay? So basically what I'm going to write, the work done in any cyclic process is equal to how much? Area under which graph, guys? How to write now? Tell me. I'll write AC, then I have to go to B, then I have to go to what, guys? D, and then I have to go to A. Do you agree, guys, with this? Are you okay with this? Just check.
Yes, sir.
Okay. So what is this? If I want to ask you, okay, and you're going to answer me, right? You're going to say work done in any cyclic process, right, is nothing but equal to what? Area
enclosed under the curve.
Area inside, right? Area inside or enclosed, you said, no? Enclosed by what? Enclosed by the area
Curves.
enclosed by the curves. Okay, that is what we have. Okay, I think this part is clear. Okay, so this area, okay, is the representation, this area here that we have under the curve, not under, sorry, inside the curves, right? Okay, that area represents the net work done. Okay, so this is what we have in a cyclic process. So don't forget this, easy concept, but we will need it. Okay, so after doing this, okay, we have a very nice and very important topic next. Okay, and that is your first law of thermodynamics. Okay, so I will speak slowly and I think you will understand what is this first law. Not going to be difficult at all. Okay, so let's start this one. Okay, see. Let me, oops, sorry, what happened? Sorry, 1 second. Okay, yes, I think so. I have started recording now. Let me just check. Yes, okay, so I've started recording also. See, so let's start this one. Okay, very important, we will need it. Okay, very much. Say first law of thermodynamics, not difficult, I'm telling you again, so pay attention, you should be fine. Okay, and in your exam, okay, they can just ask you any topic from any small questions from this topic. Okay, so be ready with that. So first law of thermodynamics. Okay, very easy. See, let's take a gas. Okay, if I take a gas or a thermodynamic system, okay, enclosed in a cylinder with frictionless pistons, okay, this is what we have diagram right now. So this is the gas I'm taking. I can take any mole of a gas. I can take 1 mole, 2 mole, 3 mole, doesn't matter right now. Okay, first thing I'm going to ask you, okay, tell me, this gas, what do you think? They have internal energy or they don't have internal energy? What do you think right now?
They have.
They have internal energy. Internal energy. Okay, and you know the symbol of internal energy, right? What's the internal energy symbol, guys? U. Okay, so they have certain internal energy. How do I know that? Because right now they will be having certain temperature. They have certain temperature, and because of this temperature the gases are moving. They're moving randomly, but they are moving. Okay, and when they move, obviously, right, you know, they have some internal energy because of some temperature. Okay, now let's check. Okay, what can happen to the gas? Okay, see, so suppose I come and tell you that dq is the amount of heat. Look at this, is the amount of heat. Okay, let me tell you, it can be positive, it can be negative, but for the timing I'm just taking positive right now. Okay, so positive value right now. Later I'll tell you what is the meaning of negative, but let's say right now positive means amount of heat added to the system. Okay, or let's say this is the amount of heat gained by the system. So dq is the amount of heat entering the system. Okay, heat is also energy, don't forget this is also energy. Okay, so now you tell me, okay, what will happen, guys, if we supply some amount of energy to this system, to the gases? Okay, what will the gas do, guys? That's the question. Do you agree that the amount of energy that the gas gains, okay, will its internal energy remain same, or there can be an increase in internal energy?
Increase.
There can be an increase. I'm not saying all the time is going to happen, okay, but there can be increase in what, guys? Internal energy. let me write the amount of increase of internal energy. Let's write du. Are you clear, guys? What is du? Du represents internal energy or the amount of increase?
Amount of increase.
Amount of
Amount
increase.
of
Okay, it doesn't represent internal energy. Okay, it represents how much internal energy has increased by or changed by. Okay, that is what represents. Okay, one more thing. Okay, check. Do you agree that the gases, can they push the piston now or not, because they are gaining energy? What do you think, guys?
Yes, sir.
And the piston will be in the same location, or it can be moved? It
Move.
can be moved. Okay, now because the piston can be moved. Okay, if the piston can be moved, who is doing the work here, guys, right now?
Gas.
The gas is doing the work. Okay, so look at this. I'm saying that the amount of work done by the gas is how much?
dW.
Okay, so I think you're clear with dW. That's the amount of work done by the gas because it is pushing the piston. dQ is the amount of heat gained by the gas, and du represents the increase in internal energy of a gas. Okay, so now check, tell me whether it makes sense or not. Okay, see, can I say that the gas has gained 10 joules of energy? Does it make sense? Just check. Is it fine? Just an example. Okay, yeah, the gas has gained how much energy? 10 joules of energy.
10 joules.
And by gaining 10 joules of energy, the gas internal energy has increased by 2 joules. Is it possible or not, guys? Tell me. Yes or no?
Yes, sir.
It's
Yes,
like
sir.
you're giving 10 joules to the gas. Okay, now the gas is increasing its internal energy. It is becoming faster. Its temperature is rising. Okay, and the remaining is how much? Out of 10 joules, already how much used? 2 joules
2
is
joules.
used to increase the internal energy, but the remaining can be used by the gas, right, to do work. That can be 8 joules, right? So look at the equation now. Can you understand? The gas gain how much energy? 10 joules. Out of this 10 joules, how much energy was used up by the gas to increase its own internal energy? 2 joules.
joules.
Plus, how many joules was used by the gas to do work?
8 joules.
8 joules. Do you agree this equation makes sense, right? Check, check. Obviously, right? 10 is equal to 2 plus 8. If I write here like this, say, if I write here 3 joules, what do you think what will happen now? Can this happen? This is correct or not correct?
Not correct.
Not correct. The gas gain 10 joules of energy. It increases internal energy by 3 joules and also 8 joules of work it has done. This is not correct. Okay. If it has increases energy by 3 joules, how much do you think it has spent in doing work, guys?
7 joules.
7 joules. Okay. So now you tell me, what is the equation? What is this? What does this represent? It represents energy or energy gained by the gas?
Gained by the gas.
Energy gained by the gas. Can I call it dq? Yes, yes.
Yes, sir.
Equals to, what is this? It represents internal energy or change of internal energy of a gas?
Change of internal energy.
Yes. So I'm going to write here du, right? Is it okay? Just check. Yes. Plus, what is this 7 joules, guys?
Work dW.
Work done. So this is dw. Is it okay, all of you guys? This is your first law of thermodynamics. Okay. What is this? First law of thermodynamics, and you can easily see, right? It is based on conservation of energy or not? It is based on conservation of energy. Energy has been just transformed into different form. Okay, it was gaining heat energy. The heat energy has been converted into internal energy, and it has been converted into work. Okay, work done, right? So this is what is your first law of thermodynamics. Okay, and any confusion, guys, here? Just check if you're okay or not with this one. Yes, yes. Waiting. All of you should respond so that
Yes.
I am also motivated, no, in teaching you nicely.
Yes, sir.
Yes, yes.
Yes, sir. Yes.
Okay, very nice. Kashish is very happy. Okay, see. Okay, see now. Okay, now see. What else can I do with this? Okay, now be careful. See, if I have an option of writing a plus 10 joules and minus 10 joules, okay, let me tell you the meaning. Okay, I think you can understand now. What is the meaning of writing plus 10 joule, guys? The heat is gained by the gas or lost by the gas?
Gained by the gas.
Gained by
by
the
the
gas.
gas.
Gained by the gas. Okay, but also what can happen? Heat can also be what?
Lost.
Lost by the gas. So you can apply this equation in both the cases, no problem. Okay, again here also we have two options, guys. I can write here plus 3 joules, or I can also write minus 3 joules. Okay, so you can understand what is the meaning of plus 3 joules. Internal energy increase or
Increase
decrease?
in internal energy.
Okay, this is decrease. Oh, sorry, this is
Increase.
increase in internal energy. Yes. Okay, and this represents what, guys?
Decrease.
Decrease in internal energy of a gas. And this also, right, can have two ways, right? I can write plus 7 joules. I can also write what? Minus 7 joules. Now what does this mean, guys? Work is done by the gas or on the gas?
Done
By the gas.
Work is
By
done by
the
the
gas. Yeah, this represents work done by the gas. And what does this represents?
work.
Work done
Done
on the gas. Okay, so see, so many ways we can look into this single formula. I can apply it to any cases I want. Okay, but only the number should match properly with the signs. Okay, so anything can happen. Okay, now let me tell you, okay, what kind of questions they can ask you from here. Okay, the first thing of course is read the statement of first law of thermodynamics. Okay, and next thing is these questions. Look at this. Okay, these questions, say, very important ones. Now we'll go to special cases. Okay, say, oops. So number A, special cases. Okay, but before that I have to show you one more thing. Can you tell me guys, what is the formula for dW? Amount of work done, small amount of work done, equals to
PdV.
PdV. Okay, pressure times the small change in volume. Okay, if there is no change of volume, what will be dV, guys?
0.
0. No change of volume is change of volume equals to 0. Okay, so dV will be equal to 0. Okay, this means no change of volume. No change of volume means no expansion, no compression. So what is the work done, guys? Automatically
0.
work done will be 0. Okay, small amount of work done or whatever amount of work done will be 0 if there's no change of volume. Okay, so just be clear with that. Okay, so keep in mind. Now I think we can proceed. Okay, so this is we are going to obviously use. So let me show you one by one now. Okay, number 1 process. Look at this. Number A process. Okay, hope I already written A. Check. Okay, let's say it is isothermal process. Isothermal process. In isothermal process, right? Tell me what will remain constant.
Temperature.
Temperature is constant. That means temperature does not change. If temperature does not change, what will remain constant for this gas, guys? Tell me. Kinetic energy remains. Kinetic energy will also be constant or not, guys?
Yes, sir.
Okay. See, if the temperature doesn't change, no, the kinetic energy also cannot change, because a gas can move faster only when the temperature changes. Okay. So if kinetic energy does not change, what will be the internal energy, guys? Will it change or remain constant?
Constant.
Remain constant. Internal energy of a gas will remain constant, because internal energy for a perfect gas means nothing but kinetic energy. Don't forget, internal energy means kinetic energy. For a perfect gas, internal energy means kinetic energy, and totally depends on what? Temperature. No change of temperature, no change of no change of temperature, no change of kinetic energy, no change of internal energy. Okay, that's how you measure your internal energy actually. Okay, for a perfect gas. Okay, so now you tell me, think and tell me, what will happen to our equation? This equation, what will be 0?
du.
Du. That means the change of internal energy will be equal to how much?
0.
Okay. What is the meaning of change of internal energy? 0. That means kinetic energy remains constant. So you think and tell me now, what will happen to our equation now? dq will be equal to what?
dw.
0 plus dw. Okay, indirectly I can write dq equals to what?
dW.
So now look at this. What does it mean? See, it's very nice now. See, it means if a gas gets how many joules? Gains how many joules?
10 joules.
Then all of the 10 joules the gas will use, right? Will it increase its internal energy or use all of them to do work?
All of them.
And there will be no increase in the internal energy of the gas. Can you understand? This is going to happen in what kind of process, guys? Isothermal process. Are you clear with what I said? All the energy which the gas gains, it does not increase its internal energy. It doesn't change its temperature. All the energy will directly go to what, guys? Or you will be used up by the gas to do work. Okay, I think this part is clear. Is it okay, guys? Can I say it's clear, all of you?
Yes, sir.
Okay, so this is the first one. Okay, so this is the first one, say. Okay, first one, isothermal process. Okay, let's go to adiabatic process, number B. Adiabatic process. Tell me what happens in adiabatic process, guys. Can the heat enter or lose or leave, or cannot do anything with the heat? What's the heat gain? So what is the amount of heat gain or loss by the gas, guys?
0.
0. So now you tell me. Okay, let's apply this formula again. Okay, this is the formula. Okay, our first equation, not first equation, first law of thermodynamics. Okay, let's apply that. Waiting, how much I'll get now? 0 will be equal to du plus dw. Is it okay? Yes.
Yes, sir.
Okay, see, I'm just applying that, no? Okay, now tell me what will happen from here. You know what? I can write like this. du will be equal to dw or minus dw.
Minus dw.
Okay, let me just take the minus on the other side, no problem. Okay, let me just write other way around, no problem. See, let me do that. See, dw is equal to minus du, right?
du.
Okay, so what does it mean? Let me tell you. See, it means that if a gas is doing 10 joules of work, just imagine, okay, the gas is gaining heat or not gaining any heat? Not
Not
gaining any heat. But if you see that your work done by the gas is how much? 10 joules.
10 joules.
That's like writing equal to how much, guys? Can you tell me how much it is equal to according to this formula? How should I write? Minus I should write.
Minus 10 joules.
Then what should I? I should write minus 10 joules or another minus 10 joules. Check. Then they will be equal, right?
Yes, sir.
The minus sign is already here. And then should I write here 10 joules for du or minus 10 joules?
Minus 10.
Then only this equation will be equal. Yes. Okay. Now what do you think it represents? Du must be equal to how much? Du must be equal
Work
to
done.
Du must be equal to what? 10 joules or
Minus
minus 10
10
joules?
Minus 10.
Yeah. So what does it
Minus
mean?
10.
Look at this. Okay. That means the work done by the gas. Okay. Work done by the gas is 10 joules. Okay. That means the gas is really pushing the piston. But if it does not gain any energy from outside, do you agree that the gas has to use its own internal energy or not?
Yes, sir.
Okay.
Yes.
That's why what does it represent? Minus 10 joules. Does it represent increase of internal energy of a gas or decrease in internal energy of a gas? Decrease in internal energy of a gas. I think it makes sense, right? Because see, the gas did not gain any energy from outside. And if the gas is still doing work, still pushing the piston, and it did a work of 10 joules, that means it must have used its own internal energy or not. And that's why there's a decrease or increase of internal energy, guys. There's a decrease of internal energy. That's why the gas is able to do this work. Okay, so I think you're clear with this part. Is it okay? Did you understand? Make sense, guys?
Yes, sir.
Okay, so this is how it works. Okay, let me show you another one. Okay, then you check. Okay, number C. I'm going to talk about isochoric process. Okay, isochoric process. Those who don't know, very quickly, simple is I'm telling you, in isochoric process, volume is going to remain constant, no change of volume. Okay, so now let's apply this formula. dq equals to du plus dw, right? If volume is constant, dv is equal to how much? 0. And if dv is 0, pdv, right, which represents work done. Okay, pdv is work done, dw
zero.
must be equal to 0. So automatically this formula will become how much, guys? dq equals to du. Okay, now you think and tell me, what does it mean, guys? It means that if the gas cannot change its volume, and if the gas is gaining 10 joules of energy plus, right, what will happen to du? What will be the value?
It will
Plus?
also gain 10 joules of.
Yes, exactly. Okay, that means if the gas is gaining 10 joules of energy, and if the gas cannot do any work, cannot push the piston, all the 10 joules will go and increase what, guys?
Internal energy.
Internal energy. Very good. Internal energy of the gas. Okay, that is what is going to happen in what process? Isochoric process. Okay, and yeah, one more thing we have. Okay, number D, cyclic process. Let's just talk about this, and I think I'm done for this topic right now. Okay, cyclic process. Okay, see now, in cyclic process, what happens, guys? A gas starts from state A, goes to which state? B, and then again it goes to which state, guys? Initial state, no? So when the gas reaches the same state, think and tell me. Okay, does it have different temperature or same temperature?
Same time.
Same temperature. Yes. Okay, the gas is going to go back and reach same temperature. If the gas is going to reach back to the same temperature, what do you think, guys? The internal energy of the gas in this entire process has changed or did not change?
Did not change.
Did not change. So there is no change of internal energy, right? In that case, what will be our formula? dq equals to du plus dw, right? So what will I get, guys? dq will be equal to dw. That means in a cyclic process, if you are giving heat to the gas, all the heat will be converted by the gas into what?
Work.
Work done. Okay, so I think this part is also clear. Okay, is it clear, guys? Just check.
Yes, sir.
Yes, sir.
Okay, so till here I think you're doing fine. So you have to know this 3 or 4 things that I discussed just now. Okay, 4 things I mean to say, These four, what are these? No notes, okay, not notes, important points about your first law of thermodynamics, okay. Now there is a formula called Mayer's formula, which they might ask you again. So your next question is this, okay. Say, I did not do it last time because we would have not be able to explain. I would have not been able to explain, okay, without thermodynamics, okay. This was in the previous chapter, but now I think this is a very good time to do this one, okay. So say, this is your topic, okay. Say, your formula is called Mayer's formula, and this Mayer's formula is nothing but this one, okay. Specific heat at constant pressure minus specific heat at constant volume is equal to how much, guys? I don't know whether you have seen this one or not, okay. If you have seen this, this is the time, okay, we derive it, okay, because it's very, very important for MBOS, to very important. CBSE also they used to ask, okay. So 3 marks, expect this to come, okay. So very, very important. Okay, check how we are going to do this one, okay. So say, I have to explain to you again what is CP and what is CV, okay. So check, say CP, if you know, right? Anybody knows what is CP? You call
Specific
it
heat at constant pressure.
At constant.
specific heat at constant pressure. I'll give you some ideas, okay. And CV represents specific heat at constant
Volume.
volume, okay. Now what are these two things? Let me just show you here. Say, I take a gas or any system, actually I keep the pressure constant. I keep the pressure constant, okay. Then you know what, I am going to measure delta Q, okay. dQ, I'll tell you what is dQ. dQ is the amount of heat required. I'm repeating again, just pay attention, okay. What is dQ? Amount of heat required, whatever is the gas I'm taking, okay. It needs some heat, no. Amount of heat required to raise is temperature by, let's say, per degree Kelvin, per degree Celsius, or let's say by 1 Kelvin. Do you agree with this thing what I wrote just now, guys? Per mole, okay, per mole I'm taking 1 mole of a gas, okay. So per mole of a gas. Are you clear, guys? What is dQ? What is
Yes.
dQ? What is dQ, guys?
Amount of heat required.
Amount of heat required,
to
yes,
raise
okay.
temperature
To do
by
what?
1 degree
To raise the
Celsius.
temperature of the gas by how many degree?
1 degree
By 1
Celsius.
unit, okay, by 1 degree Celsius or 1 Kelvin. They are same. The difference between 2 degree Celsius and 2 same okay, Kelvin units are same, okay. The difference is same. But the point is this, okay. Now check, try to understand this, okay. If I am talking about changing the temperature by 1 Kelvin or 1 degree Celsius, indirectly, right, it means I'm going to change the internal energy or not. Change the what, guys?
Internal energy.
Internal energy, right? Do you agree? Without changing the internal energy, right, can the temperature of the gas be changed or cannot be changed? Yes. Cannot be changed, okay. You have to change the internal energy by dQ amounts, okay. Then only you can change the temperature by how much? By 1 degree, okay. Or I can just take any temperature, let's say DT temperature, no problem. I don't want to take 1 degree, no problem, okay. By certain temperature called DT, no problem with that, okay. But this was under constant pressure, okay. You are doing this, okay. So let me just go to another thing now. Say, I take the same gas, you'll get me now, just give me some time. But now don't forget, okay, I'm going to keep what constant, guys, now? Volume constant. I'm going to keep the volume constant, okay. Now you think, okay, see, check. This, I kept the volume constant. Now it is again 1 mole of a gas. The same thing, same idea, not different. But this time I'm going to keep the volume constant. I'm going to supply some amount of energy again. Okay, let's call this energy dQ dash, okay. But I want the temperature to again change by how much? dt. Okay. Do you understand what I said just now, guys? Did you understand? I want to change the temperature earlier also by how much amount? dt. Now also I want the temperature of the gas to change by how much?
dt.
dt. So I have to supply heat, right? In both the cases I have to supply heat. One is I'm going to supply heat by keeping the pressure constant, and one is I'm going to supply heat by keeping the volume constant. Okay, now think and tell me, do you understand that? What is this dq dash and what is this dq? Who can tell me? Look at this. Amount of heat required, listen to me. Amount of heat required to raise the temperature by per degree, okay, per mole of a gas, right? This is called Cp or not at constant pressure. I'll write the definition. Look at this. Amount of heat required per mole per degree rise in temperature or change in temperature. Let me write dt this time, okay, not delta T but dt, no? Let me write capital T, right? Do you agree with me? This is the definition of specific heat at constant pressure or not, guys? Check. Yes or no?
Yes, sir.
Okay.
Yes, sir.
All of you agree, right, with this one?
Yes, sir.
Okay. What about in this case? What is the definition of CV? Amount of heat required to raise the gas temperature of a gas per mole per degree rise in temperature. Do you understand? This is the definition of what? CV, right? At constant volume. I think you are clear with this too, at least.
Yes, sir.
Okay.
Yes.
So you are at least clear with this one. I'm sure. I think you are clear. Okay. Let me just change. Okay. Let me just change few things. Okay. Let me not give this dash here, but let me give dash for the pressure. It's the same idea. So let me just make it dash, and let me give dash for the pressure, not for the volume. Okay. I'll do this first. I'll do this calculation first. Okay. So no problem with this. I think you got the idea. Okay. Now check. Please check. Okay. I'm going to use now something. Okay. Whether it's clear or not, please check. See. What is first law of thermodynamics? I'm talking about constant volume first of all, okay? Constant volume. Please tell me what is first law of thermodynamics. Waiting. dq must be equal to
Delta Q is
du
equal to
plus
delta U plus
dw.
delta W.
dw, okay. When the volume is constant, we already know, right? dv will be equal to how much? 0.
Zero.
That means w work done will be also equal to 0. Okay, so now according to this, I'll write dq equals to what? du.
du.
Okay. From this formula, tell me what will be dq.
du.
CV. No. From this formula, this one. CV
CV and dt.
and dt. Okay, equals to what? dq. I think this part is clear. From here to
Yes,
here.
sir.
Okay.
Yes, sir.
So I'm going to use, in place of dq, I'm going to use that. Okay. I'm going to write CV and I'm going to just write dt equals to du. Okay. And you know, right? Because n equals to how much? 1.
1 mole.
Okay, 1 mole. So I'm not going to write for other things. Okay. So I'm going to keep it equation like A. Are you clear till now? I think this part is clear.
Yes, sir.
Okay.
Yes,
sir.
This part is clear. Okay. Let's go to your pressure now. Okay. Check how am I writing pressure. Okay. See, for pressure, this one that I have already written here. Please tell me what is dq dash. dq dash according to this.
CP and dt.
Cp and dt, but again for 1 mole it's just going to look like this, right?
Yes, sir.
Okay.
Yes, sir.
Let's apply now. Let's apply first law for this case. Okay. Tell me what is first law now. dq dash must be equal to
du plus
du
dw.
plus dw. Can you understand this one? Yes or no?
Yes, sir.
Okay.
Yes,
Now
sir.
I'm going to ask you a question. Okay. The du here, the change of internal energy here, and the change of internal energy here, will they be different or same? Think and tell me.
Same.
Okay. Somebody said same. Abhijit Paul said same. Okay. What about others, guys? What do you want to say?
Same.
Same. Again, Sangam also said same. The du, the change of internal energy here and the change of internal energy here, right? They should be same. Why? Because
Temperature is same.
because temperature is same or change of temperature is same.
Sorry, sir.
Change of temperature. If the temperature you want to increase here by 1 degree, here also you want the temperature to increase by 1 degree, that means the internal energy in both the cases should increase by different amount or same amount.
Same amount.
So the du in both of them is
Same.
same. Okay, that's why I'm not using du dash. Okay, so I'm just using directly du. I think it makes sense, right, till now?
Yes, sir.
Okay, so you know what is the advantage? Look at this. Just now we got du from the volume expression. See, this du that I have, right, which is nothing but what? Cv dt. I can take and use it in this equation because they are same. Du there in the volume constant condition, right, is same as here. Okay, so now you tell me. In place of dq dash, what am I going to write? I'm going to write this one, no? Let me use this one here, okay? So I'm going to use this one. So in place of dq dash, what will I write, guys? Cp dt. In place of du, what can I write, guys? Cv dt, that I've already shown you in that volume constant term, right? Plus dw represents what, guys? pdv. Okay, when the pressure is constant, right? Okay, I think you agree with this term, right? Pressure is constant and the volume is changing, and that can happen, right? Because it is constant pressure right now. Okay, I think this part is clear. Is it okay? Did I make sense? Just check.
Yes, sir.
Okay,
Yes, sir.
check. We are almost there. Okay, check. We are almost there. See, why am I saying almost there? Because I'm going to arrange Cp dt minus what, guys? Cv
Cv
dt
dt
equals to what will I get?
pdv.
pdv. Okay, if you notice, our formula is Cp minus Cv equals to R. So I need to get R. Okay, and you all know, right? How do we get R? By writing Pv equals to what?
NRT.
nRT. This is one way of getting that R. Okay, so I will show you now how do we get this nRT and all. Okay, check. If pressure is constant, don't forget this whole thing actually represents a formula. Okay, and the work done also, right? You should agree with me. The work done I should calculate by keeping what constant, guys? Pressure constant. Okay, because this whole thing represents work calculation of the energy required when the pressure is constant. Okay, so pressure should be constant. Okay, let me use this term now. See, if I write dpv, what does it mean, guys? dpv, change of pressure or change of pressure into volume?
Change of
Change of
pressure into
pressure into
volume.
Change of pressure into volume must be equal to what? Change of nRT, right? Agree with this? Just check.
Yes, sir.
Yes, sir.
Change of pressure into volume is nothing but equal to change of nRT, right? Because this is true, so this also should be true. Okay, just now I told you, right? This pdv actually represents what? Work done by keeping the pressure constant. So when I apply here, the pressure is constant. Okay, if pressure is constant inside this, right, do I have to find the change of pressure or no need to find the change of pressure?
No need to find
Because the change of pressure is going to be equal to how much?
0.
0.
Okay, so change of pressure is going to be equal to 0. Okay, so what do I get here, guys? Tell me. Pressure will be out of this. I don't need to calculate the change of pressure. I just need to calculate what, guys? Change of volume equals to what? Look at this and tell me, what are the things constant here?
N
nR. So
NR.
nR directly comes out. I simply can write nR dt. Okay,
dt.
and for 1 mole of a gas is just going to look like what? R dt. Okay, so in place of pdv I can obviously write what, guys? R dt, and that is what I'm going to do here. So, okay, so let me just remove it. This one gone. So I'm going to get R into dt. Okay, now you can check easily, right? On both sides, what is common? dt, dt, dt. So you can cancel. So you have proof Cp minus Cv equal to how much?
R.
Okay, this is your Mayer's formula. Okay, and yeah, if you want to calculate in from calories, if you want to convert into joules, you can just divide by J. No, I'm to say 4 point that number. Okay, okay, I don't want to talk about this one right now. Later it should be fine. Okay, so at least I hope so you will study this one. It's not very difficult, very simple one. I'll send you the note on this, so study directly. So don't forget what we have done. We have calculated the amount of heat required. You can check here. Amount of heat required, this one, per mole per degree rise in temperature by keeping the volume constant, and that is what we call Cv. And where is it? This is also jumping. Okay, where it is? Oh, here. Okay, and this is the amount of heat required to raise the temperature per mole per degree rise in temperature, but keeping constant pressure. So this is our starting, and everything else will come into picture once we start writing your first law of thermodynamics in both the cases. Okay, so I'm writing here also, and I'm writing in the case of constant pressure also. Okay, so please check. Okay, now you have to understand this also. Say, what is the meaning of Cp minus Cv equals to R? By the way, do you know the value of R, guys? Anybody knows the value? Yes, anybody knows?
314.
8.314. What will be the units? Joules per
Mole per Kelvin.
per mole per Kelvin. Okay, this is the unit of R. Okay, and what do you think? R is a positive number or negative number?
Positive.
R is a positive number. Okay, so if I'm getting Cp minus Cv equals to a positive number, okay, What does it indicate? Tell me. Cp is greater or Cv is greater?
CP is greater.
Cp is greater.
greater.
Okay, now there's a time. Okay, this is a time to understand. Okay, or think. What is the meaning of Cp is greater compared to what? Cv greater. Look at this. It means heat required per mole per degree rise in temperature by keeping the pressure constant is greater than what? Heat required per mole per change in temperature by keeping the volume constant, right? This is greater. Okay, what does it indicate, guys? What does it mean? To raise the temperature, right? You need energy. By keeping pressure constant also you need energy. By keeping volume constant also you need energy. But which case you need more energy, guys, to raise the temperature?
Pressure.
By keeping the pressure
Yeah.
constant.
When pressure is constant. When pressure is constant, okay, you need more energy, more heat energy, okay, to increase the temperature. Okay, compared to what? It is more, no? Compared to what? Compared to the heat required to increase the temperature by same amount, but by keeping what constant? Volume constant. Does it make sense? Did you understand why the heat required by keeping the volume constant is we need less heat, right, to increase the temperature when the volume is constant, and we need more heat to increase the temperature when the pressure is constant. That is the meaning of Cp greater than Cv, and we can see from here. Okay, the moment you write no Cp minus Cv equal to R, indirectly it means Cp is greater than Cv. That means we need more heat energy to increase the temperature by when the pressure is constant, compared to we need less energy to increase the temperature of any substance when the volume is kept constant. Now you think and tell me why it happens. Who can tell me the answer? I'll be very happy.
So because when volume is constant,
Very good, very good. When the volume is constant, look at her, what she's saying. Okay, when the volume
when the
is
volume,
constant, what happens?
so all the heat supplied to the system is used to
Very good.
increase the
Internal energy, yes or no?
internal.
Yes, look at what she's saying. Look here. When the volume is constant, this one say, constant volume, all the heat given to the system, where does it go? It goes to
Internal.
increase in what? It goes in increasing the internal energy. Yes, that means all the heat will go and directly increase what? Temperature. Do you agree with this, all of you guys? Check. Yes or no?
Yes, sir.
Because the gas is doing
Yes,
any
sir.
work or not using any energy for work? Not using any energy that you give to the gas to do work. All the energy is used by the gas indirectly increasing the internal energy. That means only temperature changing. Okay, so now check. But look at this in your pressure, right? What happens? All the energy goes in increasing the internal energy, or the gas also does work?
Gas also.
Yes,
That
also
means you are supplying energy, but all the energy does not go to internal energy, right? Some of the energy also goes to what?
In doing work.
In doing work. That means the internal energy increases or increases slowly here.
Slowly.
So the temperature will rise as equal as that the first case, or it will rise slowly? It will rise slowly. Okay, it will not rise like a constant volume condition case. Okay, that's why what should happen? You tell me. You have to really supply what, guys? More and more energy, so that even if the work is done by the gas, now you have attained the same amount of increase of internal energy, or not, guys? I think you understood what I'm trying to say. Okay, so
Yes, sir.
did I make sense? Did you guys understood?
Yes, sir.
Okay. Waiting for some more response so that we can proceed confidently, guys. Yes, waiting. Bajirul is
Yes,
clear.
sir. Yes, sir.
Okay, Kashish is clear. Okay, Jyotimoy is also clear. Okay, fine, you understood. Okay, Aisha is also clear. I can see You guys are responding. Ronika is also there. John Shika also understood. Okay, fine. Okay, let's do this one. Okay, so for the time being, your question will be this: you have to derive Mayer's formula. Babak also says 100% sure. Okay, fine, good. Okay, Cp greater than Cv. They can just ask you to prove that Cp is greater than Cv. You have to just derive this formula only. You have to prove this one. So you have to do this derivation. I'll send you the notes later. Your job is to just now study. Okay, I'll do one more topic today. Not everything, just a bit of it. Then I'll stop. Okay. See. I know, otherwise you guys will get bored. Okay, so let me just talk about this one. Say, next question is this. Okay, not question, but this topic. Say, the question is heat engine. Okay, the question will come like this: what is a heat engine? Draw a block diagram. Okay, block diagram for a heat engine, for the principle of heat engine. Actually, I'll explain to you. Don't worry, it's easy. Principle of heat engine. Then you also have to define something called efficiency of a heat engine. Okay, efficiency of a heat engine. Okay, heat engine, engine. Okay, whatever. Okay, say. Okay, I'll answer you one by one. Okay, these are three. Okay, then you have to do some numericals also. Numericals after this, based on efficiency. Okay, so efficiency symbol we are going to use eta. It's not n. Okay, it is stylish n. You can see. Okay, now say numericals also. Okay, so very quickly let's do it. Okay, then I will give you break. No, not break, I will stop. Okay, so please till then you just pay attention. Say, all these things will come in your exam, so that's why, okay, you have to pay attention. Okay, if you want to really pass easily. Okay, without tension, if you want to pass. Okay, now say, first of all, what is a heat engine? Let me tell you. Okay, heat engine is a device, anything which can convert, okay, heat into what? Heat into
Mechanical energy.
Okay, mechanical energy, or let's say motion. Mechanical energy has to do with motion. Okay, so mechanical energy, if there's a device, right, which can convert mechanical energy into heat energy into mechanical energy or motion, right, then that device we are going to call it what, guys?
Heat engine.
Heat engine. Okay, example, can you give me some example of heat engines?
Or a car engine.
Car, yes, agree, right? Petrol burns in the car or not, guys? Petrol burns in the car and produces heat. And then
The piston moves.
piston moves. Okay, and what about the other one? Tell me some more example. Car is correct. Don't say bike. Bike is also correct if you want to say. What else, guys? Yes.
Sir, steam engine is also
Steam
like
engine
car.
also, yes. Steam engine. Very good. Okay, you have seen that movie. I forgot. Shah Rukh Khan used to dance on top of train. No, the train is what engine? You have not seen that song?
Steam engine.
Steam engine. Okay, I forgot the name of the song. Right? I forgot the lyrics also. Anybody knows wants to sing can sing. Okay. Yes.
Chaya.
Oh, Chaya. John C. Khan knows. Okay. So see, but the concept is what? Concept is that is not running on what? Petrol. No, that is a steam engine. Okay, steam is what? Steam is very hot. No, it is gas. It can make things move. Okay, your kettle also, right? It's the lid of the kettle. No, you know kettle. Yes. Kettle. You know kettle, right? And then what happens? You boil the kettle. No, let's say boil water. Not boil the kettle. You boil water. What happens to water? Water will become steam. And steam being a gas, right? Okay, and when it is hot, it is really going to go what? Going to push the lid, no? And what happens to the lid, guys? Does it stay like this, or it turns into motion? It is set into motion. The lid is going to move. Okay, you have really seen this. Okay, really seen this. Okay, okay, whatever we talk in physics, no, it's not from outer space. Okay, whatever we talk, right, you will really be experiencing them. Okay, so study like that, so it's fine. So this happens, right, and heat is producing motion. You can see that. So that's the logic behind your steam engine. Okay, then anything else you want to talk about? Anything else? In car and bikes we call it petrol engine or diesel engine. Okay, fine. Okay, this much I think is good enough. Okay, so I think you know what is a heat engine. Okay, now what is the principle of heat engine? Okay, that means what are the requirements to really have a heat engine? Okay, that is very important. Now they can ask you, and they will ask you to talk about the principle of heat engine, but you have to draw block diagram. Okay, so that is what I'm going to do. Okay, so see, principle of heat engine. Principle of heat engine. Okay, that means what are the things we really need for a heat engine to work? Okay, check now. See. So what is this? Okay, see, in every heat engine you will need working substance. Okay, do you understand this one? In every heat engine, what will you need, guys?
Working substance.
Working substance. In your steam engine, right, who's the working substance?
Steam.
Water, right?
Yes.
Water will become steam. Okay. In your car and bike, right, what is your working substance? Your fuel, no? Fuel.
Petrol.
Yes, fuel, right? What is that? Petrol only, right? Okay, just ask yourself, who is going to gain energy here or heat here? Who's going to gain energy here? Heat. Petrol, right?
Yes.
Petrol is going to gain heat and it is going to work. Okay, it is going to work, right? Here, who's going to gain energy? Water, right?
Water.
And it will work for us. Okay, it will push the lid, no? So you can think like that. Okay, so there has to be what, guys? In any heat engine you must really have what?
A working
Substance. Without that you cannot expect a heat engine to really work. Okay, then one more thing, what should a working substance do, guys? What do you think? It just should sit like that, or it should gain heat?
It should gain heat.
Very
Gain
good.
heat.
So look here, any heat engine, right, you should have a source of heat. Look at this. What is this? Source. Okay, source of what? Source of heat.
Heat.
Okay, and what should be the source of heat, guys? Okay, what should be the temperature of source of heat? It should be high or low?
High.
Let's call it T1 right
High.
now. It should be high. Okay, you cannot take energy from a cold place and expect steam engine or petrol engine to work. Okay, no. Okay, the source of heat from where the working substance is going to take the heat, okay, should have what kind of temperature, guys? High temperature.
temperature.
Okay, yes. How much energy is gained by the working substance? Now check. Okay, I'm going to represent it by Q1. Are you clear what is Q1, guys? Q1 is what? Energy gain.
by
Okay,
the working
gain by
the
working
working
substance. Yes, okay, energy gained by working substance. I think this part is clear. Everybody is clear with this. Okay, very easy concept. Okay, obviously, right? Okay, yeah. And then what else should happen? This is also very, very important. Okay, you might just not see it, but this also is very, very important. Look here. What do you think? The working substance is going to have a surrounding or not?
Yes.
Yes. The surrounding of any working substance, right? We are going to call it what? Sink. Okay. Can you imagine a working substance without any surrounding? Possible or not possible?
It's not possible.
Not possible. Okay, if you take a working substance, you cannot isolate that working substance and expect to do work. You will always get the working substance, and along with will come its surroundings. Okay, that is called sink. Okay, now you think and tell me, the sink, just like the working substance, okay, will be at high temperature or low temperature?
Lower temperature.
Low temperature. Let's call it T2. Okay, T2 is low temperature. Don't forget this. Okay, low temperature. Okay, fine. Okay, and what will happen to this sink, guys? The working substance is going to work, but will the working substance just work, or some of the heat will also be lost in the surroundings? What do you think?
Lost in the surrounding.
Lost in the surrounding. Let's call it Q2. Can you understand what is Q2? Heat lost in the surroundings. Okay, why did I say that? Let me give an example. Okay, imagine, okay, this is a kettle. Okay, very good example. Okay, this one, say this is a kettle. Okay, I don't know how have I drawn it, but fine. You are supplying heat, let's say. So your working substance is inside. Okay, water is inside. From this is the source right now. It's at very high temperature. That's T1. How much energy is going? Let's say 10 joules of energy is going. Okay, from the source. Can you understand this? How much energy is going? 10 joules. Okay, now think and tell me, will this 10 joules of energy gained by the kettle and water? No, you cannot just directly heat the water. I think you'll agree with me, right? Okay, can you just directly heat the water, or you have to heat the kettle also?
It was.
You have to heat the
kettle.
kettle also. The gases nearby also will be heated up, right? So do you think all the 10 joules supplied by the source, will it go and heat only the water, or it will heat the kettle also and the surrounding also?
Surrounding also.
Okay. Yes, yes. So do you think out of this 10 joules, all the 10 joules will go to the water, or it will not go to the water?
It will not
It will
be
not.
It will not go. So let's say 7 joule goes to the water, heating the water, but 3 joules is going where, guys?
lost to the surroundings.
It's lost to the surroundings. Okay. So can this substance, right, or working substance, can it gain all the heat and convert into energy, or it will reject some of them to the sink?
Reject some.
Yes. Okay. So look at this. Q1 represents how much heat is gained. Q2 represents how much heat is lost, and the 7 joules represents what, guys? It is representing work done by the working substance. Can you understand? It is simple, right? Say the working substance tries to take 10 joules, but it fails to convert all of them into work. So it can convert only, let's say, 7 joules out of those 10 joules into work, right? The remaining 3 joules will always be lost in the what? Surroundings. Okay, I think you got the idea, right? Okay, so let me come back here. See, so please tell me how much work is done by your working substance. Is it Q1, Q2, or Q1 minus Q2?
Q1
Q1 minus
Q1 minus Q2. I think this part is clear, right?
Yes, sir.
Okay, so this represents, okay, this diagram represents what, guys? Does it represent principal or block diagram, right? It represents what?
Block diagram.
Block
Block
diagram,
diagram.
which actually is representing what? Principle of a heat engine. Okay, there should be a source. Okay, and by the way, are you clear? The sink should be there. Is it important or not important? What do you think? Or just that I can just remove the sink? You cannot remove the sink, no chance. It is going to be there. It is an integral part of your working system. Okay, so it has to be there. No chance you can remove it. No chance you can think without this. Okay, okay. Now what is another thing? What will be your sink always be, guys? Higher or lower temperature?
Lower
Lower
temperature.
Temperature.
If it is at higher temperature, what will be the problem? Who can tell me? Higher temperature. What will be the problem?
So heat will flow from the sink to the working substance.
Yeah, and what will happen?
Work done will be negative.
No. The name sink will disappear. Okay, this sink actually will behave like a what? Start behaving like a source. Okay, so
Source
that is
of
the
heat.
change. Okay, but automatically, do you realize if I start calling source, right, what will happen to this one now?
Sink.
It will become sink, right? Do you understand? Okay, I'll give an example. See, okay, you have fire. Okay, you have fire here. You are burning wood. Okay, you are burning charcoal. Okay, you are trying to cook something. Okay, and you have burned fire. Okay, yeah. What's the temperature of fire? What do you think? Give me some example. Don't say 100 degree. Okay, 300 degrees Celsius. Okay, fire, huh? It's not water. Okay, it's fire. No, you want to cook something. I don't know what you want to cook. You want to cook soup, chicken soup. Okay, so suppose this is the soup you want to cook. No, and you have kept the container on top of this fire. Okay, so fire is burning, right? Okay, fine, very nice. Okay, your surrounding is 10 degrees Celsius. Obviously, right? What will happen? Tell me who's the sink and who's the source here for the soup.
Source is fire.
The
sink
fire
is
will be source.
sound.
Heat will be gained from here. Yes, heat will have to go from here to here, and will be lost to the surrounding, some part of it. I think everybody's clear, right?
Yes, sir.
Okay, but look at my example. Okay, very bad example. Okay, but let's try to give you. Okay, say, suppose I tell you the fire is at 300 degree, and this whole surrounding. Okay, you're cooking it inside. I don't know. Let's call it sun. Okay, sun, sun. Just imagine. You put logs. Okay, very bad example. I told you. Okay, very bad example. Okay, but you're trying to do this inside sun. Okay, just imagine. Sun. What do you think? Is the temperature same or very high temperature? 10 to
Very
the
high.
power 7 Kelvin, I think it's around this much. Okay, very high temperature. So your surrounding is hot or very hot?
very hot.
Okay, tell me, will the soup boil or not?
Yes, sir.
Yes,
Yes,
but automatically your sun will become what?
Source.
The source,
of
and
heat.
this will become your
Sink.
sink, because it is at lower temperature. No? But you understand the idea, I think, right? Okay. Yeah. Okay, so always you're always going to have certain sink. Okay, now check. Okay, I have one more last thing to talk about, then I think we can stop. I told you there is something called efficiency. Okay, efficiency. Okay, see, Idea is very simple. How much work is done by the gas ratio, okay, divided by how much heat is gained by the from the source, okay. Check. I can give you example and everything will be very simple. See, example is just now I give you. It's like this. How much heat energy was gained from the source, guys?
10
10 joules. And how much work was done by the gas or the working substance? Okay, so it is like 7 out of 10, right? And 3 of course is lost, okay. 3 is lost. So your formula is actually this, okay. N equals to Q1 minus Q2 divided by what?
Q1.
Q1, because your work done is nothing but what? Heat gain, heat lost divided by how much heat is gained, okay. So this is your formula and this is what it represents. See guys, it's like 10 joules gained from the source, 3 joules lost in the surrounding or sink divided by 10 joules gain, right? Total gain that much, okay. So out of this 10 joules, how much has been converted into useful work? It is
7 joules.
by your system, okay. So this is called the efficiency of the system, okay. I can also write in percentage. You can call it how many percentage, guys? 70%. 7 out of 10 is how much percentage? 70%. That means the efficiency, okay, the
70%.
efficiency of the heat engine right now that I've taken is how much? 70%. That means you can understand, right? If efficiency is 70% and suppose the source is giving me how many joules? 100 joules, okay. How much work do you think the heat engine can do now? Because its efficiency is how much? 70%. 70% of that will be converted into what, guys? Useful work. Can you understand the meaning of this, guys? Imagine efficiency
Yes,
to be 90%. What do you think? Is a heat engine or is a good heat engine?
Good heat
Good
engine.
heat engine. Very nice heat engine. You like this heat engine, okay? Because its efficiency is very nice. 90%. 90% of the energy gain will be converted into work. And 10% will be lost to the surrounding, okay? Now look here. One more question, then I'll stop, okay? Can efficiency be equal to 1, guys? In other words, I'm asking you, can the efficiency be equal to 100%? 1 means how much efficiency? 100%. Efficiency 1 means how much work is done and how much heat is gained, okay? For efficiency to be equal to 1, okay, do you agree that what should happen? For efficiency to be equal to 1, what should happen, guys?
Work done would be equal to
Work done should be equal to what?
Increase in internal energy.
Increase in internal energy or heat gain?
heat
gain.
absorbed.
Work done.
So like there should be no sink.
Yes, wait a minute, okay, yeah. For efficiency to be 100%, what should happen, guys? First tell me that.
The work done should be equal to the
Work
heat
done
gain.
should be equal to the amount of heat gained.
Gained.
Okay, it's like efficiency equal to, you have gained 10 joules and all the 10 joules should be what? Should be converted into?
Used.
Should be used, or let's say converted into work. But is this possible or not possible?
Not possible.
Not possible. Why it is not possible? Because for the efficiency to be 1, okay, what should happen? W must be equal to Q. And if W is equal to Q1, okay, Q1, what should happen, guys, in this formula? Check. N equals to Q1 minus Q2 by what? Q1, no? In this formula, if it has to be equal to 1, what should be 0 here, guys?
Q2.
Q2 should be equal to 0. Is that possible or not possible for Q2 to be 0?
0.
Can you
Not
construct,
possible.
okay, just think, can you construct a system whereby all the heat only goes to the working substance and no heat goes to what? Surrounding. Can you construct that? Is this possible?
No, sir.
If you can really do this, okay, you might just get Nobel Prize, okay? So I don't know, okay? If you can really do this, okay, please do it, okay? I should not say, but normally what we find is what? It is not possible for all the heat to be converted into what? Work, and the amount of heat lost to the surrounding is how much? Not possible. That's why what cannot be equal to 1, guys? Efficiency cannot be equal to 1, or efficiency cannot be equal to how much percentage, guys? 100%. Okay, 1 means 100%, huh? Don't forget that. 0.7 means what? 70%, right? Okay, so this one I'm going to stop right now. I think you got enough ideas, okay? Next day we will meet, okay? So I think we'll be fine, okay? Next day, I think, which is the proper day, guys? Which day you want to meet?
Sunday.
Sunday. Oh yeah, Sunday we have a date. Yes, Sunday. What timing we is to meet? 7, no?
8.
No, not 8. I think 7. 7 we used to make. Manba, you're okay with 7? Where is Manba? Manba is already there. Manba left already. Alright, this boy also deadly, okay. This boy also will appear and disappear very nicely, alright. Okay, Duffy has joined. I was checking. Duffy has joined from St. Margaret's. Okay, Prayasto is not coming offline, right? Other your friends? Sambhav is coming. Prayas is not coming. Okay, fine. Okay, we'll meet next time. Okay, bye. I'm done.
Sir,
Yes.